So this is the basic idea behind the word-to-vec model. We have the input x based on the training data, all are one hot encoded, and we will be multiplying it with the weight matrix and getting the corresponding embedding. And so this weight matrix is randomly initialized at first, and we will be training it based on the cost function. So these weights are trainable, and after getting this embedding, we can use any downstream model to predict the class. So we have a downstream task. In this case, we have to predict the disease class based on the node embedding. So and we can use any downstream model. It can be logistic regression, random forest, and even neural networks. So I'll be using another I'll be using the neural network here to be my downstream model. And if you got to go through the deep learning basics, deep learning models have two main methods. So one is the forward propagation, where you'll just be multiplying the input with weight matrices, and that input will be passed on to the second hidden layer, again to be multiplied with the weight matrix, and finally you get to apply an activation function to do the final loss function calculation. So we will be using the softmax activation here, since each data point in the training data set is has only a single label. So one node will be in the input and the next node will be in the output. So there is only a single node, and softmax and the softmax activation makes sure that the output probabilities sum up to 1, and the corresponding entry in the output vector with the maximum probability will be the context node ID in this case here. So and we should also implement the backpropagation algorithm to make sure the weights are trained according to the downstream tasks that we are giving here. And so first we will be taking the gradient of the loss function with respect to the activation from the with respect to the outputs of the previous layer. So here we will be using the cross entropy loss function, and so this is based on the chain rule here, and you can if you have the softmax and cross entropy loss function in your final layer, this will be your gradient with respect to the previous layer inputs. And this, so finally we want the gradient of the loss function with respect to W2 and W1, the weights in our model, and basically you will be again applying the chain rule here to get the gradients. So I will be implementing the word-to-vec model from scratch. I will be implementing a class here which will taking the vocab size or number of nodes as input, the embedding size that you want as number of, and the embedding size you want, the learning rate that basically controls the step size in your gradient descent, number of epochs you need to train the model for, and the random seed. So and I will be initializing weights based on the standard normal distribution here. So this will be the first W1 matrix corresponds to the embedding layer. So the size of the matrix will be the vocab size times the embedding size, and I will be using another hidden layer to convert the embedding size back to the vocab size, so that the loss function can be computed. So after I will be, when you initialize the class, you will also be initializing the weights of the model, and this is how the forward propagation is implemented based on the steps shown above. And this is how you implement the softmax function, and the backprop function also takes in both the input features or tokens and the labels as input to perform backpropagation, and this is basically how you train the weights. So and this is the cross entropy loss that you might have studied previously in your lectures, and basically for each epoch we will be performing the forward propagation and then the backward propagation, and we will be evaluating the model at each iteration using the cross entropy loss function here. So Let me run this class. I will be initializing the model, and we will train the model. It takes a while to train. If you have a lot of data points, it's better if you try to use deep learning libraries like PyTorch that has GPU acceleration. I have implemented it from scratch, using NumPy, so it is quite slower. And you might have noticed I have used just the normal softmax activation instead of the hierarchical softmax, and the gensim package has a word2vec class that actually implements the hierarchical softmax and many algorithmic advances in computation to make this training faster. So basically, after you train the model, as you can see, the loss keeps on decreasing here. You can try to train it for more and more epochs and see how how the loss becomes lower and lower as you keep on training. So I'll just stop it here at 50 epochs. You're also welcome to try it for more epochs. And basically, how do you get the embeddings? You just run the forward function on your inputs, and you'll get your embeddings here. So yeah, since it's quite slower, and it's not very practical, we'll be using the word2vec class from the gensim package here. We'll supply the list of random walks. We'll be telling the model to use hierarchical softmax, the skipgram model. So if you put 0 here, the word2vec class here tries to run on the continuous bag of words model. We'll be giving the vector size, the window size, and the minimum count of words. So if the minimum count of words is below 1 or equal to 1, the training data point will be removed. And also it has a nice implementation of multiprocessing, so to speed up the computation. Let's run it and get the embedding. Let's see the shape. Again, equal to the number of nodes and the embedding dimension. The next approach we will be looking into is called the node-to-vec approach, and this is the representative diagram of the algorithm here. So the main difference between node-to-vec and DeepWalk is the node-to-vec algorithm uses something called biased random walks. So in the unbiased random walk case, we selected the next neighbor based on random chance, and here we will be using a probability distribution to determine the next set of neighbors from the starting node. So this is the function to implement random biased walks. Again, it will be taking the starting node and walk length as inputs, and in addition we will be taking in something called the inward probability and the outward probability as input. So again, we will start by appending the starting node to the walk list, and based on the current node, we will be getting all the neighbors of the current node, and we will be calculating the outwards probability and the inwards probability, and we will be assigning weights to each of the neighbors, and based on the normalized probabilities we will be selecting the next node here. The next node is appended to the random walk list, and the current node becomes the previous node here. So this is how the random biased walk is implemented, and let's see how biased and unbiased walks differs. So this is from the same starting node with node ID 158. This is the unbiased case with walk length 10, and let's see here how the biased walks looks like. The special case in the biased walk is it can the node can interact with itself based on the inverse probability. So the biased walks actually contain self loops here. So again, we have the biased random walker class implemented for us in Karate Club. Let's do it. Get the box. Again, run the word2vec model, and there is another difference from node2vec and DeepWalk. Instead of hierarchical softmax, the node2vec algorithm actually uses negative sampling to actually decrease the number of data points in the training data set, so it basically removes non-informative data points from the data set and then runs the word-to-vec model. So we got it. Let's see the embedding here, word-to-vec, got the embedding and the shape. That's it. So after implementing all these methods, we have to do a comparison between all these embedding methods. So we'll be again using the human disease network dataset. I'll be using pandas library to read the labels. I'll be splitting it into train and test, and I'll be doing stratified splitting. Since it's a multi-class problem and the label proportion is not equal, if you want to get a better estimate of the performance of the node embedding methods, it's actually better to do the stratified split based on the labels, so that there is an equal proportion of labels for all the classes in both the train and test split. So the train test split is actually a method implemented in scikit-learn. So let's see what are the disease classes present here. So there is a cancer class, neurological class. So these are the disease classes that we want to predict. So given the node embedding, we want the output class to be one of these. So this is our objective here. So I have the embeddings from all the 4 methods. I'll be storing it into a dictionary, and I'll be using 3 different classifiers. One is the logistic regression, the random forest classifier, and another neural network here. So and I'll be fitting the model for each of the embedding method, doing the prediction and calculating something called the F1 score here. So F1 score is based on the harmonic mean between the precision and recall, and it gives a better estimate here in the multi-class case if the labels are not in equal proportion. It's a better estimate of performance than just using normal accuracy. I'll be running it. I'll be arranging it into a data frame here. Let's see. So we have the embedding method, the classifier, and the corresponding F1 score here. Let's try to visualize it instead of just putting it in a data frame here. I'll be using the grouped cat plot function in Seaborn, and yeah. So this is basically the comparison. Laplacian eigenmaps performs the worst, and DeepWalk and Node2Vec actually outperform matrix factorization based methods. And we might be wondering, since DeepWalk and Node2Vec use such complex approaches which are stochastic in nature, these both of these approaches can actually yield better performance than matrix factorization based methods. So what do we do wrong here? So there are something called hyperparameters for these set of models. Hyperparameters being they are not parameters of any distribution. So the parameters here actually determine the performance of the model. So for example, the hyperparameters in the DeepWalk and Node2Vec case can be the window size in the word-to-vec model, or if we want to look at the random walks function alone, we can keep changing the walk length and the number of walks. More the number of walks and the walk length, we get better information about the whole graph structure, and we can play around with these things or use an optimization method. So we can either search for all the combinations of different values we give as input hyperparameters, get the performance, or also use Bayesian optimization methods which are faster and can help us get a better performance out of these 2 methods. So hyperparameter optimization is also an important method that we should take care of here. Scikit-learn actually has an implementation to perform different types of hyperparameter optimization. There are random search methods where you randomly pick up points from the input range of values that we supply to be hyperparameters. There is a grid search method which searches for all the combinations, and there is also Bayesian optimization methods implemented in scikit-learn to give us better results in a shorter amount of time, because we don't need to search in the for all the combinations of hyperparameters that give us the best performance. And with this we will be moving on to edge embedding.